a dot of light. This is what Europa has been for almost 4 centuries, a tiny source of light as weak as a 6th magnitude star. Nothing but the second moon in order of distance from Jupiter, and the smallest of the 4 discovered by Galileo in January of 1610. At the end of the 19th century, it was possible to estimate for Europa a diameter of about 3,100 kilometers, comparable to that of our moon. It was therefore legitimate to think that it was a very similar body, arid and very craterized. It was only in the 60s, thanks to the first spectroscopic studies, that it was suspected that its surface was instead covered with ice. Then the final word went to interplanetary probes and the first missions to the outer planets of the solar system. It was Voyager 1 in March of 1979 to photograph for the first time closely the Galilean satellites, in particular Io, Ganymede, and Callisto, while Europa, which was more out of sight during the overflight of the probe, had to wait for the arrival of Voyager 2 in July of 1979. And the first high-resolution images of Europa showed ice plains furrowed by thousands of dark streaks that overlapped like a giant reddish net spread over the entire surface. But from the very beginning, something even more extraordinary was noticed, namely the almost complete absence of impact craters. Some were detected, but not in the number that one would expect from a planet without or almost without atmosphere. In their place, instead, only those long scars, which sometimes stopped abruptly, indicating that at that point the surface was somehow torn, making the darker material rise from the inside. At this point, the crucial questions had become at least 3. 1. Why were so few impact craters visible? 2. Why did the surface crack like that? 3. What was coming out from inside the planet? Needless to say, all 3 issues should have been resolved together. Since it is completely unreasonable to believe that Europa has few impact craters only by chance, there was only one other hypothesis that could be put forward to explain the phenomenon. That is that the planetary surface has been remodeled over time by particular geological events. In other words, the satellite had to be still geologically active, which meant that there must have been a permanent heat source inside Europa. The first clues in favor of this hypothesis came from considering the so-called Laplace resonance, a particular phenomenon of gravitational interaction between Jupiter, Io, Europa, and Ganymede. In practice, the periods of revolution of these satellites are integer multiples. This means that every time Ganymede makes an orbit around Jupiter, 7.2 Earth days, Europa makes 3.6 Earth days, and Io 1.8 Earth days. This particular way of orbiting around Jupiter causes gravitational perturbations that, by periodically stretching the satellite in all directions, result in tidal effects that produce heat and mechanical effects of high proportions. This, for example, is the same cause of the very intense volcanic activity of Io. But it has been calculated that even the interior of Europa could be so hot that the ice melts below the surface, already over 10 kilometers deep. And so it was that, although it may have seemed like a crazy idea, the astronomers began to seriously think that under the frozen crust of Europa could really hide a large liquid ocean. This was confirmed by the Galileo probe, which had flown over Europa a dozen times since December of 1995. Taking thousands of extraordinary photos, and had mainly measured in the layers immediately below the ice blanket the gravimetric values compatible with a density similar to that of water. Salt water, more precisely. A real ocean, 100 kilometers deep, and with a volume at least double that of all the terrestrial oceans put together. Later, what at the time appeared to be as a peculiarity of Europa, the presence of an ocean of water below the surface, was also found on Ganymede, the largest moon in the solar system, and Enceladus, Saturn's satellite. But at the time of discovery, the exceptionality of the thing prompted NASA and ESA to design exploration missions to reach the surface of the satellite, which at that point was becoming one of the hottest targets in the exploration program of the solar system. This interest was dictated not only by the concrete hypothesis of the ocean of water, but also by the possibility that on Europa there could be an environment similar to that of the hydrothermal springs present on Earth in the depths of the ocean. More accurate observations conducted in 2013 by the Hubble Space Telescope had in fact allowed to identify steam geysers very similar to those previously found on Enceladus, which had reinforced the hypothesis of the hot ocean and especially the possibility of hydrothermal microbial life. On the surface, moreover, spectroscopic analysis suggested that the long reddish streaks could be interpreted as deposits of magnesium sulfate. In practice, the saline residue of water brought to the surface by the geysers, the ideal substrate for the growth of organic molecules. These characteristics made Europa one of the most interesting places in the search for microbial chemosynthetic life, the synthesis of organic compounds carried out by bacteria in the absence of light. But over the years, partly due to the discovery of other worlds with similar oceans, and partly due to the economic crisis that has reduced the budget of space agencies, interest in Europa has been declining, and exploration projects using probes have almost all been abandoned. The only one left and recently confirmed is the one that foresees the launch by 2025 of a NASA mission called Europa Clipper, consisting of a spacecraft that orbiting Jupiter will be able to make 44 close flyovers of the moon. Europa Clipper should arrive on Jupiter by the end of this decade, and then eventually will be reached and assisted by the ESA mission Jupiter Icy Moons Explorer, which will fly over Europa twice and Callisto several times before entering into orbit around Ganymede. From this joint mission, we expect confirmations and assessments on habitability and the possibility that the surface may allow a future human settlement. But designing a mission for the colonization of a remote celestial body is obviously something much more complex than simply sending an interplanetary probe. If for the Moon and Mars we can reasonably assume that permanent bases will be implanted within the next decade, for the colonization of Europa, the expected time frame is at least 100 years, unless one of the probes that are about to leave cannot confirm the presence of life, albeit at the microbial level. In that case, you can bet sending a manned mission to Europa would immediately become a priority, and the time would probably be halved. In short, everything will also depend on the motivations of that particular historical moment. But what could be the way to bring a team of 5 or 6 technicians and scientists to the orbit of Jupiter, which on average is 2 million times more distant from the Earth than the Moon, the only celestial body on which we have set foot so far? Bring them down to Europa, give them the opportunity to build a base with accommodation and laboratories, provide them with sufficient food supplies for years, and equip them with machines to generate energy and research tools. To think of being able to do all this starting from Earth with a direct trip without using intermediate colonization stages, Moon, Mars, asteroids, presupposes that we have a capsule powered by nuclear propulsion engines and not chemical or ionic engines like those of today, able to bring the astronauts to their destination in 6 months at most. Not to mention that the manned mission should be preceded by an automatic mission capable of bringing a rover to the surface to make sure that the minimum conditions for survival actually exist. But the colonization of Europa would present other numerous difficulties. A human being on its surface, for example, could not survive the lethal radiation emitted by Jupiter's magnetosphere, a dozen times more intense than on Earth. To overcome this problem, settlers would have to settle permanently at least 3 meters below the frozen surface. Apart from the inconvenience, this could also be convenient to have easier access to water and to isolate themselves from the low temperatures reached on the surface of the Moon, on average around minus 100 degrees Celsius at the equator. However, the magnetic field of Jupiter could also be a problem for the proper functioning of electronic equipment and solar panels, as well as the low solar energy supply, 30 times less than that arriving on Earth, due to the great distance of the Sun. Having the foresight to settle near a geyser, however, settlers would have a continuous source of water, which could also be used to obtain oxygen breathable by the process of electrolysis, heat, and energy. In addition to ascertain the presence or absence of life, researchers would have the opportunity to analyze the water brought to the surface by the geyser, without having to drill the ice to get to the salt ocean. But all this, we repeat, would be addressed in a short time only if the motivational drive was reinforced by the certainty of going to study, for the first time, an alien life form. We do not believe it is possible that such an expedition could be organized before 100 or 200 years from now if the goals were generally exploratory or directed to the search for raw materials unattainable on Earth, such as helium-3. It is estimated that 25 tons of this isotope used in nuclear fusion reactors could meet the annual energy needs of the United States, but picking it up in Europa would not make much sense since it is also found in quantity on the Moon. In fact, the costs would be absolutely prohibitive since simply sending the automatic probe, Europa Clipper, will eventually cost about $4 billion. To make a long story short, compared to other potential places of colonization, the Jovian system is very far from Earth. As such, the transport of the crews and all the heavy equipment needed to build a colony would take a long time, as well as the missions where resources are transported to and from the Jovian moons. As a result, colonial ships would have to be much larger and heavier and would require advanced propulsion systems to ensure that they make the journey in a reasonable amount of time. The missions to and from the Jovian moons would also require bases between Earth and Jupiter to provide supplies and reduce the costs of individual missions. This would mean that permanent outposts would have to be established on the Moon, Mars, and most likely in the asteroid belt before any mission to Jupiter's moons could be considered feasible or convenient. This will of course be done, and the day will come when we will also establish ourselves on Europa, but this will not happen according to our forecasts before the year 2150, as long as we have explained, and as we hope, the discovery of life factor does not intervene to speed things up. Could we colonize the big cratered moon Callisto? In this video, we will deal with Callisto, one of the main moons of the gaseous giant planet Jupiter, and we will try to understand if its hypothetical future colonization is feasible or not. Callisto, together with Io, Europa, and Ganymede, is one of the Medicean satellites and was discovered by Galileo Galilei on January 13, 1610, who reported his observations in his work Sidereus Nuncius. These satellites are called Medicean because the Italian astronomer dedicated them to Cosimo II de' Medici, his benefactor. Galileo observed the Medicean satellites with a very rudimentary telescope and with a very small field of view. Even today, one wonders how he managed to discover them, given that in this very small field of view, they could hardly see all four at the same time. In Greek mythology, Callisto was a nymph, or according to other versions, the daughter of King Lycaon or of one of his sons, Cadus or Nyctus. She was one of the handmaids of the goddess Artemis, Diana for the ancient Romans, whom Zeus seduced because he was attracted by her beauty. According to some versions, inspired by the homonymous comedy by Annis, an Athenian playwright and poet, Zeus transformed himself into Artemis in order to attract Callisto and lie with her. As a result of this intercourse, she became pregnant, and when she was discovered, she was expelled and turned into a bear by Artemis or Hera. As a bear, she then gave birth to Arcade, the eponymous hero of the Arcadia region. In the last part of the myth, just before being killed by an arrow of her son, who had mistaken her for a normal bear, Zeus saved her life by placing her among the stars like the bear Greater. With a diameter of 4,818 kilometers, Callisto is the third largest moon in the solar system after Ganymede, diameter 5,264 kilometers, and Titan, diameter 5,150 kilometers, Saturn's main satellite. In practice, Callisto is larger than our moon, which has a diameter of about 3,475 kilometers and slightly smaller than the planet Mercury, whose diameter is 4,879.4 kilometers. The surface area of Callisto is 7 times smaller than the area of the Earth's surface. The circumference of Callisto is equal to 15,000 kilometers, the terrestrial one to 40,000 kilometers. The fastest airliners on Earth travel at 850 kilometers per hour. It would take 2 days to travel the entire circumference of the Earth, while on Callisto, this time would amount to just 17 hours. Would you like to try this experience? Write it in the comments. Its average density is 1.85 grams per centimeter cubed, corresponding to about half the lunar average density and 3 times lower than the terrestrial average density. This density value suggests a composition of approximately equal parts of rock material and water ice, with traces of volatile ices such as ammonia. The percentage of mass of ice present is 49 to 55%, while the rocky component is not known exactly, although it is probably similar to the composition of ordinary L and LL chondrites, which are characterized by a low content of metallic iron and a more abundant presence of iron oxide than H chondrites. Callisto's surface has an albedo of about 0.2, that is, it reflects 20% of the sunlight it receives. The surface composition is believed to be substantially similar to that of the rest of the satellite. Spectroscopic observations in the near-infrared revealed the presence of water-ice absorption bands at wavelengths of 1.04, 1.25, 1.5, 2.0, and 3.0 micrometers. Water ice appears to be ubiquitous on Callisto's surface, with a fraction of the total mass of 25 to 50%. The high-resolution analysis of the near-infrared and ultraviolet spectra obtained by the Galileo spacecraft revealed the presence of several non-frozen materials on the surface, such as iron and magnesium hydrosilicates, carbon dioxide, sulfur dioxide, and possibly ammonia and various organic compounds. The spectral data also indicate that the Callisto surface is extremely heterogeneous on a small scale. Small, bright areas formed by pure water ice are mixed with areas formed by a mixture of rock and ice and large, dark areas of non-frozen materials. Callisto's surface is asymmetrical. The hemisphere facing the direction of the orbital motion is darker than the other, contrary to what happens on the other Galilean satellites. The darker hemisphere seems richer in sulfur dioxide than the other, in which carbon dioxide is more abundant, an element that seems to be associated with many recently formed impact craters, such as the Lawton crater. Generally, the chemical composition of the surface, especially that of dark areas, appears to be similar to that of Type D asteroids, whose surfaces are covered with carbonaceous materials. Callisto is the most heavily cratered natural satellite in the solar system. Unlike neighboring Ganymede, which displays varied terrain, Callisto does not exhibit evidence of plate tectonic-like activity. Although these are two relatively similar objects, Callisto seems to have had a simpler geological history. In fact, the impact craters and rings concentric with them represent the only structures present on Callisto. There are in fact no large mountains or other prominent features. This was probably due to the nature of the surface. The sliding of ice in geological times has obliterated the craters and the largest mountains. Impact craters and multi-ring structures, escarpments, and associated deposits are the only major features found on the surface. Playing hide and seek at the bottom of never-illuminated craters would be one of the first hobbies of future astronauts who will colonize Callisto. What do you think? Write it in the comments. The surface of Callisto is dominated by two huge structures. Valhalla, the largest, has a bright central region 600 kilometers wide and concentric rings that reach 3,000 kilometers in diameter. The second, Asgard, has an external diameter of 1,400 kilometers. There are also chains such as the Gipol-Katina, a long series of impact craters in a straight line on the surface. The origin of each of them is due to the impact on Callisto of objects captured by Jovian gravity and then fragmented by the tidal forces of the planet. The crust of the satellite has been assigned an age of about 4.5 billion years, thus dating back almost to the formation of the solar system, while the concentric ring structures have an age between 1 and 4 billion years, depending on the sources considered. Its average distance from Jupiter is about 1,882,700 kilometers, equal to 5 times the mean distance between Moon and Earth, and this makes it the outermost of the Galilean satellites. Its rotation is synchronous. This means that Callisto takes the time to complete a rotation on itself and an orbit around Jupiter. Specifically, it takes 16.7 days. In other words, on Callisto, a day lasts as long as a year. It follows that one face of Callisto is always facing Jupiter, while the other always faces the other side, as is the case with our Moon. Callisto travels an almost circular orbit and very close to the equatorial plane of Jupiter, with eccentricity and orbital inclination that undergo variations on a time scale of centuries due to solar and planetary gravitational perturbations. The eccentricity varies from 0.0072 degrees to 0.0076 degrees, while the orbital inclination is around 0.192 degrees. Callisto's dynamic isolation implies that it was never significantly affected by gravitational tides, and this affected its evolution and internal structure. Given its distance from Jupiter, the flow of charged particles belonging to the Jupiter magnetosphere reaching its surface is quite low and has had negligible effects on it, unlike what happened on the other Galilean satellites. The level of radiation on Callisto's surface is equivalent to a dose of about 0.01 rem per day, 7 times less than the level of radiation that the Earth receives. Here are some reference values of the radiation levels for comparison. 0.14 rem per day, normal dose at sea level, coming from cosmic rating and natural radioactivity of rocks. 50 rem per day, typical dose assumed for a 2.5-year Martian expedition outside the Earth's magnetosphere. This level of radiation increases the risk of developing cancer by 1% each year, more or less the same as induced by smoking. 75 to 200 rem in 30 days. The human body cannot repair cellular damage caused by radiation quickly enough. Nausea, fatigue, hair loss, malformations in children, cancer in later life can occur. 500 rem, fatal dose. Up to now, there has never been a serious medical emergency in space, partly for the short distances from Earth, partly for the periods spent in space largely not exceeding a few months. Conversely, common ailments from space, constipation, nausea, headache, bone pain, etc., have always been on the agenda and managed without major problems. In the case of long-duration missions, such as a trip to Callisto, common medical risks will be minimized by careful screening and vaccinations before flights. But the exposure to radiation, much greater than that which could be experienced on a trip to Mars, and to the reduction of gravity, as well as unexpected accidents, will constitute an unknown not yet well defined. According to the old protocols, a small mission of 4 to 6 people should include a doctor. However, in a larger mission of about 20 people, the presence of a paramedic or nurse is also desirable, which would also make surgical interventions possible. If you were to be chosen to colonize Callisto, what activities would you apply for? Write it in the comments. The idea of including a medical and surgical robot managed by a crew member trained with help from Earth is being studied. But here too there is a problem, namely the delay with which the signals travel due to the speed of light, which is very large but not unlimited. Communications between the ship's medical officer and the Earth would be interspersed with long waits. How would you behave in the event of an unforeseen event during a major surgery, while you weren't able to communicate with Earth in real time? Write it in the comments. In the hypothesis that a solution to these problems is found, where could a colony be created on Callisto? Considering that the basic idea is to try to exploit as much as possible the materials present in situ to build habitats and structures for a human crew, one possibly would seem to be to build the base inside craters rich in water ice, such as, for example, the aforementioned Valhalla. In this way, in addition to building materials for the colony, the crew could have an equally important resource, water, which could be obtained by melting the ice. The frozen water present at moon poles could also be used to produce oxygen for the crew. In practice, the water molecule would be split into hydrogen and oxygen. Hydrogen would be used as propellant, oxygen for respiration. In any case, the colony should be built on the face of Callisto from which Jupiter is visible, to allow an in-depth study of the gas giant and its surface details. In any case, before sending a human crew, it would be necessary to send habitat and supplies first. The colony would be built thanks to completely autonomous machinery and governed by advanced artificial intelligence systems. Once the base is built, other problems would arise. The first is energy supply. Due to Callisto's great distance from the Sun, roughly equal to 5 astronomical units, i.e. 5 times the average distance from the Sun to the Earth, it would be extremely difficult to use solar panels, An alternative could be the construction of a nuclear fusion power plant or the use of radioisotope thermoelectric generators, already in use on some space probes such as New Horizons or the Curiosity rover. The second major problem is waste management and hygiene within the settlers' habitat. Unlike what happens on the International Space Station, where waste is stowed and burned upon re-entering the atmosphere in cargo modules, in a closed habitat on Callisto, contamination by waste materials could soon become a huge problem. As if all this weren't enough, it will be necessary to guarantee a certain comfort to the crew. In addition to the psychological aspect of being so far from the Earth, the astronauts will also need to ensure proper daily physical exercise to avoid muscle atrophy. Due to the very low acceleration of Callisto's gravity, it is very likely that astronauts will be prone to loss of muscle and bone mass. In many films and science fiction novels, Titan, the main moon of Saturn, is presented as a world to be colonized, or as a base inhabited by strange beings, or as a colony inhabited by terrestrials in exile. But could Titan's conditions be suitable for hosting humans? Would it be possible to colonize this world? And why is Titan interesting from this point of view? In this video, we will try to answer these questions. Titan is the second largest moon in the solar system after Ganymede, one of the main Jupiter satellites, and is even larger than the planet Mercury. It has a diameter of about 5,150 kilometers, while the diameter of Mercury stands at just over 4,879 kilometers. Titan is the main satellite of Saturn and was discovered by the Dutch astronomer Christian Huygens with a refracting telescope of 57 millimeters in diameter and 310 millimeters in focal length, who called it in Latin Luna Saturni. It was the first natural satellite to be discovered after the Galilean satellites of Jupiter. The current name Titan was proposed by the astronomer John Herschel, son of the more famous William Herschel, in honor of the Titans of Greek mythology. Titan travels its orbit around Saturn in about 15 days at a distance of about 1,221,830 kilometers from the planet. This distance is equal to just over 3 times the average distance between Earth and the Moon. So if you left from Saturn traveling at the same speed as the Apollo lunar spaceships, to reach Titan, you would take roughly 10 days. In short, a long journey, but after all still feasible for a holiday out of town, if you're already in the neighborhood of Saturn. But pay attention, leaving from Earth to Titan, the matter is very different. We remember that Saturn is located about 9 astronomical units from the Sun. An astronomical unit is defined as the average distance between Earth and the Sun, and is equal to about 150 million kilometers. So Saturn is 9 times farther from the Sun than the Earth, and this journey takes a few years. The NASA Cassini probe, named in honor of the Italian astronomer Giovanni Domenico Cassini, a great scholar of Saturn and its rings, was launched from Earth in 1997 and entered into orbit around Saturn only in 2004. So how do you go about taking a human crew there? Whatever form of propulsion you choose has pros and cons. For example, you could use rockets like the current ones, whose technology is already available and above all well tested and reliable. But the con is that you have to transport large quantities of fuel, and this translates into the need to build large tanks, which add a lot of weight to the ship. And if a spaceship is heavy, it is much more difficult to take off from Earth. An alternative could be to use a thermoelectric radioisotope generator, such as those of the Cassini spacecraft, based on the decay of radioactive isotopes. But here too a problem arises: how to protect astronauts from the radiation produced by such thrusters. Furthermore, unlike a robotic spacecraft like Cassini, a manned space mission has much more complex needs. For a very long period, in the case of Titan, 7 years, it is necessary to guarantee water, food, oxygen in the right quantities for survival. And this translates into the need to build a spaceship large enough to carry adequate supplies. However, there are at least 2 other major problems concerning interplanetary human spaceflight: radiation and the psychological aspect. As far as radiation is concerned, as long as a spaceship or space station is in a low orbit around the Earth, they are quite sheltered from cosmic rays and solar radiation, because they are still located within the Earth's magnetosphere. But once you get out of the Earth's magnetosphere, it is believed that if absorbed in massive doses and for long periods, such as during an interplanetary journey, in the long run, cosmic rays and other radiations could cause the onset of more or less serious diseases. But to date, this aspect is not yet well clear. The other big question concerns the psychology of astronauts. Studying the behavior of astronauts aboard the International Space Station, it emerged that to admire our planet from the cupola, a window module with 7 portholes built entirely in Italy, is essential for their mental well-being, to feel somehow at home and to suffer less isolation from their friends and relatives during their long months in space. But what might be the astronauts' reaction while traveling in interplanetary space to reach Titan? On such a long journey, isolation is much more challenging, also because these hypothetical astronauts for years would not see any other person outside of their crew members. Moreover, the same communications with the Earth would be quite difficult. If you wanted to send a message to your loved ones from Titan, it would take about an hour and 10 or 15 minutes to arrive. And the same goes for the answer. To probe the psychological effects of long-duration space missions, terrestrial simulations of mission to Mars, such as Mars 500 or High Seas, Hawaii Space Exploration Analog and Simulation, have been carried out for several years now. A group of specially selected people live for several months or even a year in conditions of total isolation, in habitats in remote places to reproduce the conditions present on Mars, living exactly as a real astronaut would do. That is, they eat rehydrated food, send and receive messages with a delay of 20 minutes, the same as with the Red Planet. In the case of Titan, it would be more than an hour. They ration supplies and energy. They cannot have direct contact with the outside, and if they venture outside the habitat, they must wear a heavy spacesuit. Also, if any accidents happen, they need to be able to handle it on their own. To increase the sense of isolation, from Titan they would see the Earth only as a small blue dot, lost in space, and the same sun seen from that remote world would appear about 10 times smaller than how we see it from Earth. Titan has a synchronous rotation, that is, its period of revolution. Time taken to make an orbit around Saturn is equal to its rotation period. How long it takes to make a rotation around its axis. But how long does a year on Titan last? That is, how long does it take Titan while orbiting Saturn to complete an orbit around the Sun? The answer is 29 years. In practice, 1 year on Saturn or Titan equals 29 Earth years. For example, a 58-year-old person on Earth on Saturn or Titan would only be 2 years old. Its acceleration of gravity is equal to about 1.35 meters per second squared. So on Titan, you would weigh only around 1/7 of your weight on Earth. But be careful, your mass, that is the amount of matter you are made of, remains the same. Because exactly what changes is your weight, because the gravity of the celestial body which you are on changes. The surface temperature of Titan is about 94 Kelvin, that is minus 179.15 degrees Celsius, therefore rather cold, given that a very small part of the light and solar radiation that we receive on Earth reaches Saturn, and therefore also Titan, about 1%. According to data collected by the Cassini spacecraft and the Huygens lander, it has been possible to verify that the internal structure of Titan is characterized by a rocky core surrounded by layers of ice in different crystalline forms. A layer of liquid water and ammonia was also detected around the core. Thanks to the data and the spectacular infrared images collected by the Cassini spacecraft and the Huygens module of the European Space Agency, which landed on the surface of Titan in January of 2005, it was possible to assess the presence of methane lakes and channels carved from the same methane on the surface of Titan. Some of these channels somewhat resemble the canyons found in some places on Earth, such as the Grand Canyon. But the most interesting thing about Titan is its atmosphere, which exerts a pressure at its surface of 1.6 bar, equal to about 1.5 times the Earth's atmospheric pressure at sea level. Titan is in fact the only satellite of the solar system surrounded by an atmosphere, made up of 95% nitrogen, N2, and methane, CH4, for about 5%, plus traces of other molecules based on carbon, nitrogen, and hydrogen. It is believed that these proportions are very similar to those of the chemical composition of the atmosphere of the early Earth, while the density of Titan's atmosphere is greater, 1.15 times, than that of the Earth. Moreover, the atmosphere of Titan is about 10 times thicker than Earth's. This implies that the sky brightness on Titan at midday through its very thick cloud layer could be very similar to the Earth's sky brightness 5 minutes after sunset. Measurements carried out by the spectrometers on board of Huygens and Cassini probes have also detected the presence of toluenes, organic macromolecules rich in nitrogen. It is thought that they are formed by the dissociation and ionization of methane, and in the case of discrete quantities, as in the case of Titan, also from the molecular nitrogen inside the celestial body or in its atmosphere by high-energy particles or solar radiation, producing ethane, ethene, acetylene, hydrogen cyanide, and other molecules. These small molecules combine with each other to form more complex molecules, such as aromatic compounds, benzene, and other organic molecules. These complex units tend to polymerize to form an aerosol of heavier molecules, which, in the case of Titan, in addition to settling on its surface, would also be responsible for the orange mist that envelops the entire satellite. Since this atmosphere is not breathable for humans, once on Titan it would be necessary to build plants capable of producing oxygen. But how to produce the necessary energy? Given the great distance from Earth, a human settlement should be completely self-sufficient. According to a study published in 2017 in the Journal of Astrobiology and Outreach, there may be several ways to produce energy on Titan. Geothermal. It plans to exploit Titan's residual internal heat, produced by the release of thermal energy by the nuclear decays of heavy elements present in the core and by tidal interactions due to the gravitational attraction of Saturn and other low Saturnian satellites. Unfortunately, this geothermal energy on Titan is very low. Wind. The problem is that near the surface of the satellite, these winds are very weak. While they are more intense at altitudes of the order of 3 kilometers and beyond, at 40 kilometers of altitude, winds below 20 kilometers per second. To exploit these winds, bound airships or balloons could be built, or even a special wind power plant, which could produce energy for hundreds of megawatts, more or less the amount consumed by the entire population of the USA. Solar. In theory, it is a viable hypothesis, but since Titan receives only 1/100th of the solar radiation compared to the Earth, to have a sufficient production of energy through solar panels, it would be necessary to cover a very large portion of the surface of Titan, more or less 10%, corresponding to 89% of the U.S. surface. Hydroelectric. A hydroelectric power station built in the vicinity of the Kraken Mare, the largest sea of methane on Titan, with a length of 1,100 kilometers and a width of about 500 kilometers, could produce energy for a period of time between 53,900 and 431,250 years terrestrial, roughly corresponding respectively to 1,840 and 14,740 years of Titan. Chemical. It plans to exploit the numerous hydrocarbons present on Titan, using them as reagents in various types of processes to produce thermal energy and oxygen. Nuclear. Already used to power some space missions, this method of producing energy is very interesting because it is potentially capable of producing energy for decades. Moreover, the radioactive elements could be extracted locally from the rocks, rich in silicates. So to conclude, in theory, the colonization of Titan could be possible, but certainly not in the short term, because a lot of scientific new research is needed to develop completely new technologies or improve existing ones.